So, hi everyone. Welcome to today's special seminar on the topic of information, brains, and networks. I'm Albo Lu from Washington University in St. Louis. I'm so glad to host today's seminar. So this insightful seminar is initiated by the community of causal emergence and computational neuroscience within the Swarmer Club. And today we're honored to host an eminent scholar in the field, Dr. Thomas Varley, who will share his profound research outcomes on today's topic. So now, please allow me to introduce him with great honor. So Dr. Varley comes from Vermont Complex Systems Center, where is he engaged in postdoctoral work. He earned his PhD in 2023 from Indiana University, with research focusing on complex systems, networks, and computational neuroscience, and the applications of information theory in brain science. The causal emergence study group has previously shared several of Dr. Varley's papers, so those who are interested can view our past videos. So moving forward, I would like to introduce our special guest who will join us in the discussion today. So the first one is Professor Zhang from School of System Science at Beijing Normal University. He's also the founder of the Swarma Club, Swarma Academy, and Swarma Research. He's also the former special advisor to Tencent Research Institute and Huawei Strategy Research Institute. His research primarily revolved around complex system analysis and modeling, as well as the scaling theory. The second one is Professor Chen. He's also from the School of System Science and Beijing Normal University, whose research direction includes large-scale computational neural models for premise and the developmental mechanism of structural functional connectivity in children's brain development. And the third one is Mr. Yuan. He's the technical and product advisor at Swarma Research. His research interest includes causal inference, complex systems, and related field in artificial intelligence. And also, Dr. Zhang is a postdoctoral researcher at Tafts University and a scientist at Swarma Research. He earned his PhD degree in complex systems from Arizona State University, and his research direction is statistical physics and complex systems. The last one is Mr. Tian. He's a graduate student from Tsinghua University's Department of Psychology, Brain and Intelligence Lab. And his research direction is the statistical physics principles of complex systems. Yeah, so here's the content today. In today's talk, Dr. Varley will introduce his latest research from 2023. The content will include the introduction of the standard method of modeling complex systems as pairwise networks. And then we will talk about why those pairwise interactions fail to capture the high-order synergies. And this will lead into the existence of the dark matter in the networks, the shadow structures of interdependencies. Then it will also raise the crucial questions that what higher order and emergent information theory means for the future of complex systems research. Here are the two papers will be discussed today. Without further introduction, it's my utmost pleasure to invite Dr. Varley to take the stage and enlighten us with his presentation. Welcome to Dr. Varley.
All right, thank you for that great introduction. Let me share my screen here. Yes, this is, thank you very much for that very, very kind introduction. I'll be talking about the two papers that you guys had discussed previously, the Nature Communications Biology paper and the PNAS paper. And I'm sort of taking both of those papers and trying to synthesize them into a sort of a novel research direction that I have been very interested in lately, which is this problem of dark information in complex systems. And I'm kind of drawing an analogy with this idea of dark matter in cosmology. In cosmology, most of the universe is made of this stuff that we kind of know is there, but we can't interact with it. None of the tools that we have can really make it visible to us. And so dark information is something very similar. It's information, it's structure, statistical dependency in complex systems that we kind of know must be there, but we have very limited capacity to actually study directly. Although the two frameworks that I'll be talking about today, the O information and the partial entropy decomposition, are starting to get there. So I'll start by basically just reiterating this thesis that I just gave you. Then I'll jump into study one, which is the O information and fMRI data. We'll talk a little bit about what the O information is. I don't know if you guys are super familiar with that line of work. I'll talk about how we use simulated annealing to find subsystems of the brain that have, particular statistical properties. And then we'll sort of do a little short synthesis before moving on to study 2, which is the partial entropy decomposition paper. That gets a little bit more formal. And so we'll talk about why the partial entropy decomposition kind of, I think, implies that this dark information exists. And then we'll also compare that sort of formal analysis with the empirical evidence from fMRI. Again, we'll do a little takeaway. And then I'm actually going to talk about 2 other lines of research that are both sort of in this vein of information that standard tools can't really see. And that would be the failure of multiplicative interactions to differentiate between redundant and synergistic interactions. And then this idea of dyadic camouflage, which was developed by Ryan James and Jim Crutchfield several years ago. And it describes what happens when higher order interactions can kind of masquerade as lower order ones. And so I think that all of these together kind of point in this direction, that there's a lot happening in the space of higher order interactions that is largely invisible to us. And so that brings us to, the 2 sort of fundamental thesis statements of my work recently. The first is that typical tools in complex system science are preferentially sensitive to redundancy and blind to higher order synergy. And that current approaches to complex systems are missing a combinatorially vast shadow structure of higher order synergies. If you think about a network model of a system, right? Well, if you have n elements in the system, you can infer at most n squared dependencies, 1 possible edge for every pair in the network. But, if you allow for, sets of 3 triads, well, then suddenly you have n choose 3, which is a much larger number. If you allow for 5, you have n choose 5. And so if you just think about the total space of all possible dependencies that could exist in a complex system, the pairwise bivariate network is actually a very, very, very small slice of the whole potential structure. I like to draw an analogy with a book called Flatland. I had to read this when I was a student taking geometry. It's about little 2-dimensional shapes that live in a 2-dimensional world. And then one day, like a sphere wanders into their universe. And they can't really see the sphere, but it's, they can see its shadow, and they can see, how the higher dimensional structure interacts with their lower dimensional world. And so I like to think of modern complex systems as kind of like we're in flatland. We're in 2-dimensional flatland, kind of starting to get a glimpse of these higher order structures that exist in much larger and more complex worlds than we can generally perceive. So I'm going to be talking in this presentation a lot about the idea of redundancy and synergy. All right, and these are sort of 2 faces of higher order information. Okay, and I like to think about them in terms of logical conjunctions and disjunctions. So if you have a set of k elements, all right, redundancy is the information that could be learned by observing x1 or x2 or x3 all the way down to or xk, right? In contrast, synergy is the information that can only be learned by observing x1 and x2 and x3 all the way down to and xk. And like I mentioned before, most common approaches to modeling complex systems only consider pairwise dependencies, right? So you're looking at, x1 and x2, x2 and xk. This higher order stuff only happens when you start to get sets of 3 or more elements. And if you're familiar with the partial information decomposition, you know that the space of possible combinations of ands and ors can get very complicated very fast. You can have the information that could be learned by observing x1 and x2, or x1 and x3 and xk, all right? But, generally, I kind of try to stay away from those very complicated partial information atoms, and I'll be focusing mostly just on the general idea of redundancy, which is information joined by the logical or, and the idea of synergy, which is information joined by the logical and. Okay, so that gets us to study 1. Also, I should say, if anybody has any questions, I can't see the whole group, but you can always unmute and sing out, or if you want to post something in the comments, I'll try to keep an eye on that as well. So we're going to start with study one, which is the paper in Nature Communications Biology, and it focuses on this idea of the O information. Okay. And so the O information is a really, really interesting measure. It's signified by this little glyph omega. And for a multivariate system, it gives you a very efficiently computable heuristic of whether the system is dominated by redundancy, in which case the O information is positive, or whether the system is dominated by synergy, in which case the O information is negative. Okay. And so we start with this function, the total correlation, which is just a measure of deviation from independence, right? So this total correlation function is down here. It's the difference between the sum of all of the marginal entropies and the joint entropy. And it's fairly easy to see that this thing is going to be 0 when all of the all of the elements are independent of each other, right? In the case where all the elements are independent, the joint entropy is equivalent to the sum of the marginals, and this thing is going to be 0. Total correlation will also be maximal in the case where every xi is a deterministic function of every other xi. In that case, the joint entropy will be comparatively low, and the sum of all of the marginal entropies will be double counting the same information over and over and over again. Okay, so total correlation is a nice monotonic function that describes how completely a given system deviates from independence among all of its first order elements. So we take this as the foundation of our more complicated O information measure. And so on the left side here, what I'm circling with my cursor, the first thing you do is you just take the total correlation of the whole system and you multiply it by some large negative number. All right, this 2 minus n factor just kind of comes out of the math, but the result is going to be that this is going to be some large negative number. And then you're going to add back in the total correlation of all of the subsets of our system X, excluding one element. Okay, so this notation x to the minus I indicates that this is going to be every element X excluding the ith one. And so if adding all of this information back in is greater than multiplying the whole out some large number of times, then you have information that is double counted, essentially. You have information that is being added back in multiple times, and so it overwhelms the information that's in the whole. Conversely, if this number is larger, then when you add all of the reduced total correlations back in, you will end up with not quite making all that information back up. There is some information in the whole that is not accessible when you consider these subsets of size n minus 1. Okay, and so generally we don't care that much about the actual value of the O information. We just care about whether it's less than 0, in which case the structure is synergy dominated, or if it's greater than 0, in which case the structure is redundancy dominated. Okay, and this was introduced by Fernando Rosas and Pedro Mediano in a really excellent PRE paper several years ago. Let's see. This is sort of just reiterating what I had already said. The total correlation is a measure to which a measure of the degree to which the system deviates from independence. And so if the deviation from independence in X is uniformly distributed over all the elements, then the expected value of the subsets of size n minus 1 should be equivalent to just n minus 1 over n times the total correlation of X. Okay, and this gets into some interesting stuff related to the Tononi-Sporn-Edelman complexity, which I can talk about at the end if people are interested in that. I'm going to jump ahead. And so you can really see this logic here in trying to understand when does the total correlation, or when does the O information work out to be greater than 0, and when does it work out to be less than 0? Okay, so on the x-axis, we have subset size. So this is our system of size n. And we only ever really care about the case of n minus 1. And then on the y-axis, we have sort of the normalized total correlation. All right, and so the expected decrease in total correlation when you remove one element, all right, that would be that would be the difference, the sum of these two lines, the pink and the orange line. If the expected decrease in the total correlation is larger than the decrease you would get in the null case, where information was uniformly distributed over the entire system, then you end up in the case where synergy is greater than redundancy. Conversely, if the expected loss of structure when you remove an element is less than you would expect in the null case where structure is uniformly distributed over the system, then redundancy is greater than synergy. And I apologize, I realized that I mixed up the order of these slides. And so I like to think about this, the redundancy dominated case, in terms of an orchestra, right? So imagine an orchestra where every instrument is playing the same note. You know, they're all just going A, B, B, A, B. If you were to remove, say, the violins, that doesn't really change much about sort of the global structure of the music, right? All of that information is totally redundant. The expected loss of removing the violins is going to be sort of not that impactful, let's say, okay? In contrast, if you have an orchestra that is playing some very complex Bach concerto where every instrument is playing a different thing, then the consequences of losing any single instrument will actually cause the piece to become much less interesting than you might expect sort of by chance. Okay, and so that's sort of the analogy that I really like to use, is that when redundancy is like this orchestra where everybody's playing the same instrument over and over again, whereas and therefore losing any element doesn't cause that large of a change in the structure of the music, while synergy exists in this sort of interesting edge of chaos space where there's different music coming from every instrument that sort of somehow works out to be more interesting than, if you were just to sum the individual parts all on their own. So that brings us back to these TSE plots here. And so in this study, we were really interested in how the O information gave us insight into how synergy was distributed over the brain. Okay, and so what we used a simulated annealing algorithm to extract sets of brain regions of size k that had the most negative O information. And recall that when O information is negative, the system is synergy dominated. So we were using an optimization to find subsets of the brain data that had the strongest synergy. And so we used 95 human connectome project subjects, just resting state fMRI. And then we basically aggregated all the subjects and all the scans to construct sort of a master probability distribution. And we used a Gaussian estimator of the total correlation to sort of efficiently compute this without having to binarize anything. So there's a nice identity that for a multivariate Gaussian system, the total correlation is a function of the natural log of the determinant of the covariance matrix with some extra junk. And so we could use this to very quickly and efficiently estimate the O information for these continuous signals. And so, we swept over all sizes of K and tried to compute the average O information at that scale, each size K being sort of a scale. And you can see that we got this very nice U-shaped curve where approximately around, let's say, subsets of size 10, there was the was the maximally synergistic scale. And then as the subset size got bigger, the system became overwhelmed by redundancy, and eventually it became impossible to find any synergistic subsets at all, even with our optimization. The red color indicates whether these ensembles that the optimization algorithm found were irreducibly synergistic. Okay, and so we defined an ensemble as irreducibly synergistic if it was impossible to remove any element and increase the synergy. And so you can see that in the case of the very large systems, none of these were irreducibly synergistic. Because they're so redundancy dominated, you could always remove elements and increase the synergy. But down here in sort of the 3 to, let's say, 15 range, there were a large number of irreducibly synergistic ensembles. And so this tells us a couple of really interesting things. The first is that even though we talk about synergy as information that's in the whole and not any of the parts, actually, there does not appear to be that much synergy at the level of the whole fMRI scan. In fact, synergy is sort of distributed over much smaller overlapping subsystems that form what we call a synergistic scaffold. And it's also worth noting that so every dot in this plot corresponds to one run of the simulated annealing algorithm. And so you can see that there are many, for a given size k, there are many subsets that are sort of equivalently optimal, right? For a size k, you can get many subsets that, have an O information of negative 0.25, okay? So sometimes you see people talk about this idea of a synergistic core. This is something that came out of Andrea Lupi's work, but we actually found that there's not just one synergistic core, there's many different overlapping synergistic ensembles that form this sort of complex scaffolding structure. We then wanted to ask, okay, so how does the distribution of synergy map onto the existing sort of models of the brain? Okay, and so this is where we start to directly compare the O information and the sort of standard network models of the brain, right? So this was using the classic Yao systems that are often used to partition brain networks into different communities. And so what you can see is that if you're only sampling from one of the Yao systems, okay, on average, the O information is quite high. And then as you sample from two Yao systems, so half of your nodes come from the somatomotor system and half of your nodes come from the visual system, well, then then the expected O information goes down. And as the number of systems you sample increases, the O information starts to decrease as well. And so this suggests to us very strongly that these systems, that have neuroscientists have been using for years are really reflecting redundancy in the brain. Okay, that when you look at like the visual system, the reason we call that the visual system is because there's a lot of redundancy in that system. Okay, which is perhaps not super surprising since these systems are defined in terms of high density regions of a pairwise correlation network. But what was much more interesting is when you look at the fraction of ensembles that have negative O information. If you sample from all ensembles that all sit within one of the Yao systems, you find no negative O information at all. Okay. If you sample subsets that are span two of the different Yao systems, you find very little. And then as the number of systems sampled increases, the fraction of ensembles that have negative O information, that have synergy, actually increases. And so what this tells us is that not only are sort of the classic Yao systems really reflecting redundancy, but that synergy sort of lives in between these Yao systems, right? You only see it, in ensembles that have, one node in the visual system, one node in the dorsal attention network, two nodes in the default mode network, and maybe one in the limbic system, right? And if you think about sort of how complex networks and functional connectivity are explored in neuroscience, the idea that there could be anything interesting happening in ensembles that all sit in different communities is very radical and quite different from what the kinds of analyses most people do. If you take your functional connectivity network as the ground truth, you would have no idea that there was anything interesting happening in a set of nodes that spanned a bunch of communities. You would just say, oh, well, they're disconnected. But that's actually not true. They're not disconnected. They are connected, but they're connected by synergy, not by redundancy or pairwise connectivity. And so this sort of brings us to the end of the first study. Again, just reiterating the points that I've gone through. The O information provides a really nice heuristic measure of whether a given system's statistical structure is dominated by redundancy or synergy. The human brain has a lot of subsystems, at least as we see them in fMRI, that are synergy dominated, but they're much smaller than the whole cortex. They generally sit, around 10 brain regions. And there's no single sort of synergistic core where all of the synergy is sort of parked. Instead, it's distributed in a decentralized fashion over the cortex in the form of these overlapping synergistic systems. And then once again, synergy sits between canonical pairwise networks like default mode or somatomotor, whereas redundancy overlaps with, and actually, as we'll see in a moment, sort of drives these canonical pairwise networks. So we worked most of this out in 2022, published it in 2023, and I was very happy with all of these results. Obviously, I think they're very cool, but there are a number of sort of questions that were left unanswered by this work, okay? And the one that really bothered me the most is that the O information is really this heuristic measure of whether synergy or redundancy dominates, okay? But, dominates is not the same thing as being entirely comprised of, right? Just because a system has, an O information greater than 0 doesn't mean that there's no synergy in it. It just means that there's more redundancy. And so I really wanted to figure out, is there a way that we could try to untangle, the redundancy and synergy and see them both at the same time, as opposed to just figuring out, where was there more redundancy or where was there more synergy? And so the natural first step for this kind of project would be something like the partial information decomposition. And my understanding is that you guys have already read a number of papers about this. And so I'm going to go through this rather quickly. I love that I can assume that. Like, I usually have to spend like hours going through this, but it's really nice to have an audience that's familiar with the PID already. But for those of you who are not, the PID is a framework by which you could decompose the mutual information that a set of sources discloses about a single target, in this case, all of our X's disclose about Y, into various redundant and synergistic atoms, okay? And so in the case where you had, X1 and X2 jointly disclosing information about Y, you would partition that into the redundant information about Y that you could learn by observing X1 or X2, the unique information about Y that you could only learn by observing X1, and the synergistic information about Y that you can only learn by observing X1 and X2 simultaneously. And then, you have the marginal mutual informations follow the same kind of pattern. And I have to shout out the PID analysis was first proposed at Indiana University, where I did my PhD, by Paul Williams and Randy Beer. So that was really fun to sort of get to talk to Randy and talk to him about where all this came from. I'm sure many of you guys have seen this Venn diagram before. It's just a very visual way of representing the bivariate PID, right? So you have the redundant information is in the middle. It's the overlap between these two circles. Each circle is the mutual information that one element discloses about Y. So the redundancy is the information about Y that could be learned by observing X1 or X2. The unique information is the difference between the marginal mutual information and the redundancy. And then the synergy is all this extra special stuff that can only be learned when you observe X1 and X2 together and not any of the simpler subsets. And so I focused on the bivariate PID here because it's good for building intuition, but in point of fact, the PID can be used for any number of sources onto a single target Y, okay? Unfortunately, the PID requires making a distinction between sources and targets, right? This is the mutual information that X1 and X2 disclose about Y, right? This requires you to partition the system into the source elements and the target elements, which isn't really what we were doing with the O information. If you think about it, the O information is just computed directly from, the covariance matrix. It has no notion of sources and targets. So I needed to figure out some way that we could sort of decompose the structure of the system sort of qua itself, okay? And so what we're going to do is we're going to play kind of a neat little trick, okay? We're going to use the PID, but we're going to make the target element the joint state of all of the source elements, right? So there's a very well-known identity that the mutual information between a set of elements and their own joint state is just the entropy of that joint state. And so when you pipe this mutual information through the PID, what you end up with is a decomposition of the joint entropy of the whole system. And so here our sources are the elements of the system, and our target is sort of the system itself. So, in a very fundamental way, we are decomposing the information that all of the parts disclose about the whole, right? And in true PID fashion, the sum of all the atoms will be the entropy of the whole. And so what's really cool about this is that you can actually use this to decompose analytically the structure of more complex information theoretic quantities. So for instance, let's say you have a 3-element system. Okay, it's got x1, x2, and x3. You can break that down into the 18 partial entropy atoms, and then you can actually, build back up a measure like the mutual information as a linear combination of these partial entropy atoms. And that kind of falls out of the fact that, there's the entropy of the joint, and then you can also decompose the entropy of the subsets. And, because of the structure of the partial information lattice, those two, the marginal entropies and the joint entropies are comparable. Okay. And so, the first thing that you're going to notice is that even though the mutual information between x1 and x2 is a pairwise measure, it includes the redundant information that's copied over all 3 of the elements. Okay. And then you also have the information that is redundantly copied over the x1 and the x2. Okay. And so already you're seeing that even though this looks like a pairwise measure, there is some higher order information sneaking in. And so if you were to sum the mutual information, x1 onto x2 plus x1 onto x3 plus x2 onto x3, then this triple redundancy term is going to be triple counted. Okay. And even worse than that, you also see that you have to subtract off a bunch of synergistic entropy terms. So, the information that is shared between x3 and the joint state of x1 and x2 actually counts against the information that x1 discloses about x2. So, the state of x3 is relevant in here. We just sort of don't see it when we're just looking at, the mutual information and sort of the usual Shannon formulations. Okay. And so this, I think, partly explains some of what we saw in the O information results, right? That, these regions of dense pairwise connectivity, the Yao systems, the visual system, the somatomotor system, well, all of these dense regions are going to be multiply counting, whatever redundant information is shared between all of the elements in that system. And so, it may be that when you look at the dense region of the functional connectivity network, you're not actually seeing lots of truly pairwise relationships. What you're actually seeing is you're seeing a higher order redundancy that is contributing to the apparent density of the pairwise network, because higher order redundancies count towards lower order mutual informations. You might ask, well, okay, can we sort of get rid of this higher order redundancy by conditioning, right? This is a very common operation in statistics and in network inference. You say, okay, well, I want the information that x1 discloses about x2 conditioned on x3. If you were doing like a classic linear regression, you would call this regressing out, right? Under the hood, they're very similar. And so if you decompose the mutual information that x1 discloses about x2 conditioned on x3, you do get rid of that pesky sort of triple redundancy term, but suddenly now all of these higher order synergy terms have been added to the measure. Okay, and so the higher order information, like in a fundamental mathematical way, really cannot be escaped, right? Either your pairwise measure is double counting lots of higher order redundancies, or if you condition, you're adding in lots of higher order synergies, right? It's actually very hard to get a true measure of pairwise dependence, and all of the functional connectivity analysis that has been, going on in computational neuroscience for the last 20 years or so hasn't really reckoned with this fact. We never really understood it until we had the tools required to actually think rigorously about these higher order measures. Okay, so there's no escaping higher order information. It's either redundancy inflating the density of your network, or it's synergy being revealed by conditioning or regressing out. And so, we can bring this back also to the O information, since it's possible to write the O information out in terms of joint and marginal entropies. We can actually kind of use this as a sanity check, like, oh, is the O information actually telling us what we think it is? And yeah, the answer is it looks pretty good. So for 3 elements, you can see that the triple redundancy has a positive valence. So, the more triple redundancy is, the more strongly positive your O information will be. And then all of these higher order synergy terms are negatively counted, right? So if all of these together dominate the triple redundancy term, then O information will be negative and synergy is outweighing redundancy. It's kind of odd that the triple synergy actually counts towards positive O information. We double checked that math a bunch of times, and it's obviously true, but we're not 100% sure what to make of it. Is it possible that you could have a system that has no redundancy but still has a positive O information because it's purely synergistic? We don't really know. So working on this is sort of something that we've been talking about doing for a little while. But by and large, we can see that the O information does behave the way that Rosas and Mediano initially proposed that it must. Excluding this weird little synergy term, redundancy counts towards positive O information, synergy counts towards negative O information. So that's nice, kind of gives us a little bit of confidence in the last set of results that we published using the communications biology paper. So, we have some, I think, pretty strong formal arguments that higher order interactions are compromising pairwise functional connectivity data. But, can we also get some empirical evidence for this as well? And so here we use the same 95 HCP scans, same 200 brain regions, concatenated. And unfortunately, this time we had to binarize about the median because the redundant entropy function that I developed at the time could not be applied to continuous data. So this did require binarizing, but again, we had concatenated so much data that I was very confident in the robustness of the joint probability distributions. And then, so what we did is we computed the pairwise functional connectivity network, as well as doing the complete partial entropy decomposition for each of the million-ish triads, so sets of 3 in the system, and 1 million of the tetrads, so sets of 4 in the system. And then we directly compared the pairwise density in the functional connectivity network and the community structure to this higher order information that involves 3 or more elements. And so what you can see is that, both for triads on the top row and tetrads on the bottom row, that there's a really strong correlation between redundancy and the mean functional connectivity, for that triad, right? The more redundancy there is, in a triad or a tetrad, the more tightly connected they would appear to be in the pairwise functional connectivity network. And these are like insane Pearson correlations. This is like 0.999. I've never seen anything like that. And conversely, you can see that synergy, particularly in the tetrads, actually suppresses mean functional connectivity, right? The more synergy there is in a system, the less likely it is to appear to be integrated in the functional connectivity network. And you also see this in the triads as well, although the effect is not nearly as strong. I played around a little bit with sets of 5, and you see the same effect as well, but the combinatorics are so obnoxiously large that you can't do it at scale. And then, if we also look at the communities, we see a very similar kind of effect. So here again, we have tetrads on the top and, triads on the top and tetrads on the bottom. And so we can see that, if you look at these cumulative probability curves, all of the triads that sit within one community on average have higher redundant structure, right? And then all of the triads that span 2 communities, well, they have lower median redundant structure. And then finally, triads that sit between 3 communities have almost no redundant structure. And you can see the same thing with tetrads, right? One community has the highest median redundant structure, 4 communities has the lowest redundant structure. And again, conversely, tetrads where all the communities sit in, all the nodes that sit in one structure have the lowest synergy. And then when you're sampling communities where every tetrad, where every node sits in a different community, there you now have the highest synergistic structure. And so this is almost exactly the same result as we saw in the O information, but instead of just looking at redundancy synergy dominance, we're actually looking, for a given tetrad, we can extract its redundant structure and its synergistic structure and compare them face to face. But the same global effect appears that, synergy is highest in those subsets that all sit between different functional communities, whereas redundancy is highest in all of those subsets that sit within functional communities. So this is yet another line of evidence using a very different mathematical approach that functional connectivity structure is really preferentially sensitive to redundancy and does not see or is even anti-correlated with the presence of synergy. Again, reiterating the same thing that we saw in the communications biology paper. And so that's sort of the takeaways for this. Once again, synergy sits between communities and is invisible or even anti-correlated with standard pairwise analyses. And so this is what sort of prompted me to start thinking about this idea of the shadow structure. That when we looked at the pairwise methods, the functional connectivity network, there really seems to be a bias in how the higher order information was represented. Redundancy was, very much sort of driving the structure of the pairwise FC network, whereas synergy, was sitting between the structures in the network in sort of these hollow places that, would never be recognized as interesting by the network sort of network science community. And so, that information that, is invisible to the functional connectivity network, that's the shadow structure. It's all of the higher order dependence that is invisible to the standard lower order approaches. And so we looked at networks. I do have some results also looking at manifolds using things like PCI. I don't talk about them here, but you see the exact same effect as well. The manifolds, the first two principal components are almost entirely driven by redundancy, and then synergy is way out in the low variance explained principal components that nobody ever looks at. And so that, is basically a very, very quick and dirty summary of my PhD dissertation and the work that I worked on. But I'm not the only person to have worked on this. And I also had some other stuff that I had done previously that I really hadn't sort of recognized for what it was until I, started thinking about this idea of the shadow structure. So I'm going to talk you through two more sets of results that don't involve fMRI at all, and I think really sort of generalize this idea and make it sort of a broader critique of how we think about higher order interactions in complex systems generally. Okay. And so the first one I'm going to talk about is going back to the partial information decomposition. I'm going to ask, how does it compare to another standard approach for looking, this time explicitly at higher order interactions in complex systems, which is multilinear regression with a multiplicative interaction coefficient. Okay, so if you talk to a psychologist or you talk to an economist, you say, hey, I want some notion of the interaction that, X1 and X2 have with a target Y, the first thing they'll do is probably reach for linear regression with multiplicative interaction coefficient, right? And so the idea is you want to predict Y as some function of an intercept plus, linear coefficient on X1 plus a linear coefficient on X2 plus some linear coefficient on the product of X1 and X2 plus some error term, okay? And there are many, many, many different ways you can go about estimating these things. Almost any, mathematical programming language has a bajillion tools for doing this, okay? And so my question then is, what does this multiplicative interaction term tell us about the structure of the interaction between X1, X2, and Y, okay? And so to do that, I generated some synthetic data. This was part of another sort of largely unrelated project, but I generated some synthetic discrete data that followed either a purely redundancy-dominated information structure or a almost entirely synergy-dominated probability structure, okay? I made very large data sets by sampling from these distributions, and then I just piped them into the sort of multilinear regression function in Python stats models package. And what I found was that, it was always able to see some higher order interaction, right? Whether it was higher order redundancy or higher order synergy, but there was almost no way to tell which of the two higher order interactions was which, right? So on the left, you have the redundant data, and then on the right, you have the synergistic data. And if you just look at these coefficients, these betas, they're all highly significant. There's nothing really that obviously different about them, particularly with respect to the multiplicative interaction term, right? They're both positive. They're both about 0.13, 0.14. If I were just to hand you these two linear regressions and say, okay, which one came from a synergy-dominated system, which one came from a redundancy-dominated system, you would have no real way of knowing. Okay. And so, this, I think, generalizes this problem of the shadow structure, like even beyond the space of pairwise network inference, right? Because even the standard tools that, social scientists use when they are trying to infer higher order interactions still lack the power to disambiguate between redundancy and synergy, these two sort of flavors of higher order interaction. Okay. And then finally, I have to acknowledge I'm not the first person to notice this. Way back when, like 20 teens, two scientists who I really, really admire, Ryan James and Jim Crutchfield, they introduced this notion of dyadic camouflage to refer to higher order synergies that kind of masquerade as lower order correlations. Okay, so just to reiterate where we've gone so far, we've seen that the pairwise network approach to looking at complex systems doesn't really work if you have lots of higher order interactions. Then we looked at the multiplicative linear interaction coefficients, which does attempt to, go beyond pairwise and actually look at higher order interactions. And that doesn't really work either because you can't see the redundancies or the synergies and disambiguate them. And then finally, I'm going to argue here that what Jim's and Crutchfield shows that even when you are just using sort of off-the-shelf multivariate information theoretic approaches to higher order interactions, sometimes still the measures fail, right? Sometimes still the higher order interactions are too complex to understand. And so what they did was they built two probability distributions, each of which contains 3 bits of information, but they're distributed over the elements x1, x, y, and z differently. Okay, in the dyadic distribution, the 3 bits are all pairwise. Okay, so this would be truly represented as a pairwise network. And then they have a triadic distribution, that has what is this? I think 1 bit in an XOR gate like structure, and then 2 bits in a copy like structure. Okay? And what's really cool about these two distributions, I have no idea how Ryan James worked this out, is that even though they are fundamentally different, one is pairwise dyadic, one has a higher order synergy in it, almost every information theoretic measure sees these distributions as being identical. So for instance, if you look at the entropy diagrams for the triadic and the dyadic distributions, you see it looks the same, right? It looks like there's just all 3 bits of information are in pairwise mutual informations. That's true in this case. It is not true in this case. So this is what they call dyadic camouflage. And actually, they constructed these in such a way that almost every information theoretic measure of structure is identical for the dyadic and the triadic distributions, right? You're looking at entropy, you're looking at mutual information, you're looking at Tononi-Sporns-Edelman complexity, you're looking at some of these I've never even heard of, right? But you can just go down the list and you can see 0 bit, 0 bit, 3 bit, 3 bit, 3 bit, 3 bit, 1.5 bit, 1.5 bit, 0, 0, right? Almost all of these information theoretic tools, some of which were designed to assess multivariate interactions, cannot actually disambiguate between the dyadic and the triadic distribution. Really, there were only 2 that could. And then the one that I really care about is the partial information decomposition, specifically using Bertschinger and Rao's measure. It was the only one that could differentiate the dyadic distribution where it correctly ascribed the information about Z to independent, unique information from X and Y, and the triadic distribution, where it saw 1 bit of synergy and 1 bit of redundancy, which again, if we go back here, is the correct formulation. And so where does this leave us? Okay. In a really like in a space that is both, I think, frustrating, but also quite exciting, right? You know, I hopefully have convinced you that standard approaches to using just networks to model complex systems fail to represent synergies and double count these redundancies. Um, and that specifically the synergies, seem to appear in those areas that the networks are particularly insensitive to. But that, even if we go beyond the pairwise network, other measures of explicitly higher order interactions, such as the multiplicative interaction coefficient, can't actually, get us to where I think we want to be, which is disambiguating between synergistic and redundancy. And even if we go into the information theoretic space, we still might not be correctly parsing the higher order interactions because of this idea of dyadic camouflage. There's actually very, very few techniques that exist out there that can really give us a sense of what the higher order interactions look like, right? It's at this point basically the PID and its derivatives. This means that, we are standing in front of this incredibly large space of higher order interactions. Like I said before, way, way larger than the space of pairwise interactions. And we've got like a little flashlight, right? This is sort of like the PID or the PED. And so that means there's a lot of stuff to explore, but it also means that we're going to have to think really hard about how we develop new tools to actually explore this space and understand it, because many of the things that have been developed over the course of the 20th century are just completely unequipped to make sense of this, all of this dark information that, we're just starting to understand is out there. And so that brings me to the end of my presentation. I hope I didn't run too long or ultimately went too fast. I gotta give a huge thanks to my mentor, Olaf Sporns in the middle, and then my two closest collaborators, Mrs. Maria Pope on the left and Dr. Josh Vaskowitz on the right. Also Dr. John Beggs, Dr. Kayo Seguin, and Dr. Maria Gracia Pukshadu, who were, great mentors and friends. And then I've been supported for the last 5 years by the National Science Foundation, the Complex Networks and Systems Research Traineeship at Indiana University. And so that's the end. I'm happy to answer any questions, or if we want to jump right into the discussion, I'm totally flexible.
Okay, great. Thank you so much for your excellent presentation. Yeah, so according to our previous schedule, we're going to talk about the question listed in the shared document, but actually I realized your content today is a little bit different from
May
those
I
two.
ask you a question?
Yeah, of course.
Yeah, thank you. Thanks for your talk. I think it's very nice, and we know there are lots of dark matters actually hidden in the complex systems. But one slide I'm not so clear, so please explain more. You mentioned about the community structure and the relationship between the community structure and higher order redundancy and synergy. Can you move to that slide?
I'm just going to keep going back. When you see it, just tell me.
Okay. Community structure.
I think it's in study 2, the end of study 2.
Yeah, maybe. Yeah.
End of study 2, this one?
You mentioned that actually a lot of redundancy information is in the community.
Yeah.
But yeah, but a lot of synergetic information is a kind of a new network structure, but I'm not so clear what does it mean.
So I mean, we're not clear on that either. We're still trying to figure it out. But let me go into these a little bit more detail. So here we have the functional, we computed the pairwise functional connectivity network, and then we computed lots and lots of groups of 3 and 4. Okay. And then we used a multi-resolution consensus clustering algorithm on the pairwise functional connectivity network to assign every node to a community. So then we can take, a given set of four regions and ask, okay, well, are all 4 regions in the same community? Are all 4 regions, in 2 communities? Or are they all in different communities? And so, you typically have redundancy is highest when everybody sits within a community, and synergy is highest when everyone sits between the communities. again, what exactly that means, I think the simplest explanation is that whatever synergy is, okay, and I'm a little bit fuzzy on this myself, if I'm being totally honest. Whatever synergy is telling us, it is not being reflected in the structure of the pairwise functional connectivity network. All right. And so perhaps, if you think that synergy refers to some kind of integrated information, some kind of, Tononi style phi concept, well, then maybe what that tells us is that the functional connectivity network is actually not the best way to think about integrated information because, for mathematical reasons, it's kind of not well represented by the structure of the pairwise functions. Maybe you think that synergy is just noise. And actually the reason that synergy is highest between the communities is because there's actually no structure there. I don't really believe that. I think that there is interesting stuff happening in the synergy, but a lot of how you are going to interpret this result will depend on sort of what you think synergy is really about, what it's trying to tell us. And that's something that I'm, open to discussing because I don't think anybody has, again, we kind of know that it exists. We know that it must exist. But, I think there is still a lot of uncertainty about, how do we interpret this in a biological context? What is this telling us about, the brain as a organ, not just the brain as a complex statistical structure? So hopefully that kind of answers your questions.
Yeah, can I understand as just because community network community of the actually cannot distinguish between synergistic structure and redundant structure. Am I right?
So the network community is preferentially biased towards redundancy. When you see a dense region of the functional connectivity network, what we think is happening is that there's some, let's say that you have a set of five nodes, right, that are all connected, all interconnected in a functional connectivity network. We think that what's happening is that connection, that set of, 25 edges or whatever, is actually reflecting the presence of a fifth order redundancy that, is getting counted over and over and over again in each of the pairwise correlations.
So
the structure of the functional connectivity network, and by extension, the structure of the communities in that network is really only telling us about redundancy. It's not telling us much about synergy.
Oh, I see. Yeah. So synergy is a very small part, actually.
Well, sort of. It's if you look at the values, right? So here the redundancy, is 0.05 bits to 0.07 bits. Here the synergy is like 1 bit to 1.3 bits. So there's actually a lot more synergy than there is redundancy. It's just kind of invisible in the network. It's, in all of these combinations of nodes that, span different community structures.
Okay, so what is the size of the synergetic structures? Is dominate or this is
so you can see this
size
this is in bits.
Bits. But how about the size of the nodes? How many nodes?
Oh, so this is all 4 nodes, and this is all 3 nodes. So because the partial entropy decomposition scales very badly, we couldn't go for more than about 4 nodes. But we could sample, if you think about, we have 200 brain regions, we can sample a lot of sets of 4. There's 200 choose 4 possible sets. So we can sample a lot of them to get very good estimates of these distributions.
Oh, okay, thank you.
Can I ask a question? So in what timescale you are studying on? Because intuitively, if your timescale is very small, the interaction is quite local, like a pairwise interaction. But if you expand your timescale, like a few steps, more than one step, and then the effect is spreading over the entire system. So did you see any trend that when you increase in time scale, the synergy increase or not?
So we didn't look at that. We basically considered every frame of the fMRI scan to be sort of like a draw from like sort of a random draw from some distribution. That's a really good question, though. And I'll be thinking about it now, but no, we didn't look at any of that.
Okay, thank you. I think we also before your talk we discussed about a connection between synergy and invariant quantity. So, for example, if X, Y, and Z they have some synergistic information, then you will find maybe you might find a invariant quantity that can only be computed from X and Y and not from any subset of them. So have you studied any topic on this?
So that one of the things that we were looking at, and I'm not 100% sure this is totally related, but one of the things that we were interested in was this idea of frustration in like a spin system. So if you have something like an Ising model, right, all of the little magnetic fields all want to be pointed in the same direction, right? They all want to be going up or yeah, or down. Or, and then there's other combinations, like you could have like two up and one down or something. But then there are some configurations that are sort of frustrated, right? They're higher energy and they don't, and they're not typically stable, right? They're not in the lowest, they're not the configuration that is the lowest energy state. And so if you were to look at those, that's where you see a lot of synergy in, in a spin system. So I'm not 100% sure if that's sort of what you mean by invariant quantity, but yes, it seems to be that redundancy happens when the systems are sort of happy at their lowest energy state. And then synergy happens when you have these sort of frustrated or far from equilibrium configurations that are, typically not super stable. But again, that's not using brain data. That's just like simulations using, Ising models and things like that.
Oh, that's quite counterintuitive. Although it's different from what I mentioned, but this is also very interesting.
Yeah, Daniele Marinazzo has some papers about this, looking at synergy and spin systems, which is very very interesting stuff.
Thank you.
Harry, I have a little question about the details of your latest example. Can you hear me clear?
Yes.
Yeah, for your latest example, there is so many measurements for the two situations. Yeah, and I noticed that what is the key? Seems different for the two situations.
Yes, so K is the only other measure that worked. So I talked about the PID. The K measure, I'm blanking on the name. I think it's called the connected information. It's something that what is the guy's name? I'm totally blanking on his name. Bill Bialik worked out, and it has to do with the difference between maximum entropy distributions. So if you look at the information in the whole and then subtract off the information from like the maximum entropy distribution consistent with all the lower order pairwise margin, all the lower order marginals, that is the connected information. And it also was the only other measure that worked. If you were to search Bialik connected information, or you were to look at this this paper, James and Crutchfield, they cite it and they discuss it, but it has to do with maximum entropy distributions.
Okay, thank you very much.
Hello, Dr. Varley. May I ask a question?
Yeah, go for it.
I want to first ask a question about your first work. It's actually the definition, the concept of O information is quite interesting and kind of intuitively understandable. It's kind of we're talking about something these elements should be totally synchronized, but not should and also
I think we lost you.
Yeah, I think you are muted.
then I should type my questions in the chat.
Sure.
I also see that Yang Qian asked a question, so I'll get to that. Actually, I'll try to answer that while you're writing your question. Is that okay?
Yeah, sure.
Okay, so it says, I have a technical question. When we need to do PED on some extremely high dimensional variables, let's say 10,000 dimensional variables, is it possible to do MEDIC? No, actually. So the PED and sort of by extension, the partial information decomposition scale very, very badly. Okay, so if you think about the PID in the two sources onto a single target, you've got 4 information atoms. Okay. If you have 3 sources disclosing information about a single target, you're going to have 18 information atoms. If you have 8 sources disclosing information about a single target, you're going to have like some number that is like 30 digits long. That number of information atoms. It scales with a sequence called the Dedekind numbers. So there is no way that you can do the PED on a system larger than about 5 elements. The O information scales very nicely. We've taken the O information up to hundreds of elements. But if you have thousands or tens of thousands of elements, you're going to have to get creative with how you formalize these notions of redundancy and synergy. And I don't think anybody has quite worked that out yet. So I'm sorry to be a bearer of bad news, but the PED is not the tool that you're looking for in this context.
Okay, I changed my internet. Is this clear now?
Yes.
Okay, perfect. My question is about O information. Actually, it's quite intuitively understandable. It's we talking about elements shouldn't be totally synchronized, but not independent. So, and this O information is give us an explanation about this thing is also cannot just explained by like a combination of each element. So my question is, actually, you showed a nice figure, how it gives the calculator in the human brain. And I want to say is this all information give us a clear hint about this these regions between modules. And you show us a different combination. So my first question is about when you show this combination, have you find because it's quite different from the typical year system, and did you actually find like for those different set of regions is like different set of regions is like they work together more but not in a very totally synchronized way, but it's kind of quite interesting information way. So my question is, what are they? Have you found the most exclusive is in distinguished group of the So
let me pull up the actual paper itself, because we do have a figure. That shows what the brain regions are. All right, so this is gonna take me a moment to explain what we're looking at here. But so you can see the figure from the paper. Yes.
Sure.
Yeah. So remember that we did all of the optimizations, and then we found that subsets of size 10 were sort of the most synergistic. So then we took all of those subsets that we'd optimized, and we just counted how many times do given brain regions participate in these optimally synergistic bags, and then we project them onto the cortex here. And so what you can see is that there you do get a lot of default mode regions. You've got some of this this sort of posterior stuff happening here.
PCC, yeah.
Yeah, but then you've also got a lot of visual system, so the visual system seems to integrate, synergistically with the rest of the system. You've got a lot of, this would be sort of frontoparietal control network kind of stuff. So you are seeing, it's like somebody just took chunks of different sort of classic Yao networks and stitched them together into this pattern. And so, we're still a little bit fuzzy on exactly sort of how to interpret this particular pattern, but it seems to be pretty robust.
Okay, it's quite interesting because normally we're talking about during resting state, the brain is quite dynamic. It the synchronized pattern is varies over across time violently. So here you show some robust structure that make us wonder how it plays the rules in this dynamic changing during resting state.
One of the things that Maria Pope, who I shouted out at the end, she's still working in Olaf's lab, and she is working on time resolved, taking this structure and trying to get, a more time resolved picture of how it dynamically fluctuates. So, they're very close to having a paper that they can put up on arXiv. And so, yeah, we were thinking along the same lines. It's just going to be, a couple more weeks before that's ready to show the world.
Yeah. My second question is about your second work. Is you give a very novel definition of this redundant structure. And for me, because you should, it's meant about the 3-atom system, right? So come to the system with more elements, and the terms become more and more if we consider if it's a 4-element system, it's already many terms, but come to even high order, it's come to like if we try to understand the high order, it's become more and more complex. So intuitively, it's I wonder, can we do it like a logo? It's like a high order stand of because come to for us to understand many terms of a high order is a little bit challenge. So can we make it more like understandable, like some logo? This how is this a high order come from a low order? Is this which part belong to which order? Those kind of combinations.
Yeah, so that's something that that is something that we have not worked on, but Daniele Marinazzo and Sabino Stramaglia, both Daniele is out of Ghent and Sabino is somewhere in Italy. They've introduced this idea of a gradient of a gradient of the O information, which attempts to do exactly what you're talking about. It says, okay, how can we find some lower order representation that kind of captures the essential higher order dynamics in a way that is faithful to them. And so if you were to search for gradients of O information, you would find that. I don't know if there's a way to do it in the context of the PED. The PED scales so badly that, since we could never go above about 5, it was possible just to kind of do it all out by hand, essentially. Yeah.
Sure.
But that would be an interesting question to look at down the line.
Okay, thank you. Thank you.
Dr. Varley, I have a question.
Yeah.
We know that in PID we have some difficulty to calculate the redundancy and the synergistic information. So is that an inherited problem in PED as well, or you are?
So the PED is a special case of the PID. So yes, it inherits all of the problems that the PID does. The thing about the PID that I think is often throws people off is that the lack of the redundancy, that like there's not one unique function for redundancy, right? There's potentially many functions that satisfy redundancy. But what's really important is the axiomatic structure. If you can propose a redundancy function that has, certain properties, then the PID becomes like totally mathematically sound, right? Like there's no doubt that the lattice exists and that you can bootstrap your way up the lattice and that, the atoms will have certain values, So I know there's been a lot of debate about whether the PID is sort of, complete or whatnot. But I took great care to ensure that the redundancy function that I proposed in this paper, it does work. It induces the lattice. It's provably non-negative. It has all of the axioms that you would want to get the Mobius inversion. So if you can find a good redundancy function, then there's no problem with the PID or the PED. But if you don't believe in the PID, then you shouldn't believe in the PED either, because the PED is just the PID of the holes onto the parts onto the whole.
Okay, understand. So another question is you just mentioned that both the PID and PED scale very badly. So you mentioned a technique that you just sample a multivariate variance system into small groups. For example, if you have tens of variables, you just sampling the say 4 or 3 of them, and to do the calculation. So it's quite interesting. So the final result is the average of the sampling result. Is that correct? So
yes.
What's the intuitive of this technique? Is that does it have some very solid basis, or you just casually have this technique?
So yeah, so like for instance, this curve is the average of all of the constructed from the averages. You interpret it given the limitations of your methods, right? So if we get on average this much, do I have like an average plot? If we have on average this much O information, or this much synergy, or whatever. I mean, that's mathematically well defined. Like, it's just the expected value of this distribution, which is the distribution of the O informations or synergies over this population. But you can only draw conclusions about that particular scale of the system, right? So if you sample lots of groups of 4 and you get lots of synergy, that doesn't necessarily mean that there can't be 10th order redundancies. You just don't see them, right? So I don't think there's anything sort of mathematically dicey about it. It's just you have to think very critically about how you interpret these results, and make sure you're not overselling the kind of like how much insight you've actually gotten into the structure of the system, because you're only looking at, say, groups of size 4 or less out of a 200 element system.
Yeah, it's very interesting. I think maybe some kind of a solid method can be developed by this way.
Yes, I mean, yeah, I think I mentioned this at the end. I definitely don't think that the O information and the PID or the PED will be the last word in higher order information, right? I think we pretty desperately need people to develop new measures that scale better and give you a more fine, like scale better or give you a more fine-grained picture. There's many different ways that the O information and the PID could be improved on. We just haven't worked them out yet.
And let's go back to the definition of omega, the O information. Yes. So I haven't read the paper. So can you just explain how to intuitively to understand the 2 minus n?
So the 2 minus the 2 minus n is really weird. It falls out of just the mathematical definition. We started with a different, Fernando Rosas and Mediano, they proposed a different definition of the O information based on total correlation and this other measure, the dual total correlation. And then we showed that you could rewrite it just in terms of total correlation, which made our computation much easier. The 2 minus n comes out of the math, basically. It's just you do the algebra and this factor of 2 minus n appears. I think when I first introduced it, I was saying, what you're kind of doing is you're just taking the total correlation of the whole and multiplying it some large negative number of times, and then trying to sequentially add back in, the total correlation of the subsets. Why 2 minus n as opposed to just minus n? That I could not really give you a satisfying answer to. I wondered about it myself.
Yeah, it's quite interesting. So if X only has 2 dimensions, so this 2 minus n will equal to 0.
Yes.
And yeah, okay, thank
Total
you.
correlation is only defined for systems of size 3 or greater.
Yes.
Great. May I have a question?
Yes.
Okay, could you please go to the linear regression part? I think it's the third part, I guess.
Yes. All the way. There we go.
Like, I may have some idea about like the base of it, because the synergistic is often related to the exclusive OR. So if we change x1 times x2 to maybe a exclusive OR between x1 and x2, do you think it could be a possible way to capture the synergistic synergy?
Possibly. I haven't really thought much about how you could transform the multilinear regression into something that would be sensitive to synergy. Yeah, I mean, it'd be worth trying out, but no, I haven't thought about it in any detail. If you try it out, let me know. Let me know what you find, because it would be interesting to find ways to make the multilinear regression sensitive to redundancy or synergy preferentially.
Yeah, because as far as I know, like for the people in the quantum field, they're trying to use linear regression to capture all the data pattern, and exclusive OR is kind of classic pattern they're trying to capture. So I think there should be some base that we can explore to use the special base to capture those data pattern. Yeah.
Yeah, one thing that may be an issue is that the exclusive OR is like an inherently non-linear pattern, right? So
Yes.
I'm not sure how, like if your measure is linear regression, I'm not sure how, like it may just be sort of flawed from the outset, trying to find, this synergistic non-linear relationship in a linear regression, so I'm not saying that it can't be done, but it's a tricky problem.
I see. Maybe change to maybe higher dimension base. Could be.
Maybe, yeah.
Maybe. Okay, great. Maybe I have another question, like for the PED. The motivation for using PED is like partial information decomposition is directional, and so we want some indirectional things. Do you think synergistic naturally is a kind of indirectional high order relationship among the variables?
I mean, I think that depends a lot on how you define synergy, right? Yes, generally I think that, the directedness in the PID often feels sort of arbitrary. I think that these things are better understood as undirected sort of qualities. But, if you have, depends on your specific question, your specific application. There's lots of different considerations here.
Yeah, maybe like let me think about it in a different way. It's like, do you think synergistic is one-to-one correspondent to the exclusive OR, this kind of pattern, or there could be another pattern also belongs to the synergy?
So I mean, I think the exclusive OR is the most synergistic pattern, but it's not the only pattern that has synergy. Like almost everyone agrees that the logical AND gate has some synergy. It also has some redundancy in it. So, redundancy and synergy, saying that something has synergy is not as trivial as just saying, well, it's like an exclusive OR gate, right? The exclusive OR gate is synergistic, but you can have synergy that is not exclusive OR like.
Yeah. For discrete data, yeah, of course it's true.
Yeah.
Okay, I see. Yeah, I think that is all my questions. So, does anyone have any question?
Okay, I have another little question. I think I can understand this meanings when they are discrete variables, but I want to know if there are any gaps when you want to apply them to the continuous systems, because they have different properties.
Yeah, so if your system is Gaussian, or you're willing to make Gaussian assumptions, many of these measures do have closed form representations.
If it's not Gaussian, can we apply this framework to it directly, or?
So you can always apply the Gaussian estimator, right? You can have as any continuous data, you can compute a covariance matrix for it, right? You're just only getting the linear relationships between the variables. So if you're comfortable only getting the linear relationships, then you can use the Gaussian estimators. If you do want nonlinear, non-parametric continuous estimators, there's some measures, things like the Kraskov mutual information. There are non-parametric continuous mutual information estimators. There has not been much work extending those to higher order stuff. I think there is a non-parametric Kraskov-based total correlation function, which you could use to build an O information function. But as far as I know, there's no continuous parametric, non-parametric partial information redundancy function, for instance.
So does anyone have a question about the slides?
So I have a question about the O information. So you applied it on the brain data, and I saw this two trend of fMRI and for the region, like for the fMRI, when you're increasing the scale, the synergy ratio is decreasing, and for different brain region, when you scale up, the synergy is increasing. So I guess this is coming from core screening, but I just want to know how this O information might relate it to core screening.
So that's a really complicated question. And a lot of it, I think, depends on whether you are using Gaussian or discrete estimators of the O information. You would expect, I think, I know that you guys had Eric Hole come and talk to you, and he talked a lot about coarse graining. So, if you have lots of redundancy, like the O information is very, very positive, my guess is that you should be able to then find a coarse graining that reduces the dimensionality of the system while also, kind of removing the redundancy and sort of leaving you with perhaps a more synergistic O information. But that's not something that we've ever really looked at. I'm afraid it is 9:30 here, so I can only give you guys about 10 more minutes before I have to go to bed.
Yeah, of course. So maybe we can have a few quick questions. See if someone has some quick questions.
Yes, Dr. Varley, I'm interested that have you ever compared the interactive information with the O information? Because similarly, they have the same property or regarding the synergistic and redundancy information measurement.
So the interaction information and the O information are actually identical for 3 variables. It's the same. The math is exactly the same. I've never looked at the interaction information for more than 3 variables because I don't know, it never really made much sense to me. And the O and I don't think the interaction information for 4 or more variables preserves the structure. I don't think the sign of the 4th order interaction information is like redundancy, synergy, balance in the same way that it is for the O information.
Okay, thank you.
Okay, good. So if you don't mind, maybe we'll have the last question to see if someone have any question, or maybe we can call it a day because it's already pretty late in Dr. Varley's time. Yeah. So good. Maybe appreciate a lot. Yeah, on behalf of all the people here. Thank you so much for your excellent presentation.
Thank you very much for giving me the chance to talk about my work. And you are always welcome to email me. I think you guys have my email. So if you want to talk more or ask questions that occur to you later, by all means, shoot me an email. And yeah, I'd be really curious to hear what you guys are working on with all of this. But
Yeah.
Great.
You are welcome if you have opportunity to come to China and Beijing. You're welcome.
Yes, I would love to come to China one day. I'd love to come one day. Yeah, thank you very much.
Yeah.
Thank you.